Bien, bonjour à toutes et à tous. Donc, bienvenue. Donc, on est dans un amphithéâtre de l'Université de Montpellier qui est à 50 mètres du CINES. Et donc, je suis Michel Robert, le directeur du CINES. Je suis accompagné de Philippe Lavocat, donc, qui pilote GENCI. Donc, vous avez derrière vous donc, quelques logos donc, qui sont à la fois les GENCI, ses associés, les trois centres de calcul. Et aujourd'hui, donc, on est réunis ici pour la restitution des grands challenges ad astra. Donc, vous avez un programme qui est très dense, avec une partie en présentiel et une partie en visio. On ne nous a pas demandé, mais ça viendra un jour, de faire le bilan carbone de la conférence entre les présentiels et distanciels. Mais voilà, donc on va essayer de jongler. Et donc, je crois que tout se passera bien grâce aux services techniques de l'université qui sont là. Donc, il y a une journée précédemment organisée au CNRS sur les aspects plus scalaires. Et donc là, on va discuter de ad astra, de la partition GPU, mais aussi APU. C'est pour ça que sur le programme, on a distingué des exposés type HPC, type IA, sur principalement la partition GPU. Mais comme vous le savez, on a installé sur ad astra 2 une partition APU, qui a le mérite déjà d'une grande sobriété, d'où son classement en 3e position actuellement au Green 500, donc depuis la conférence Supercomputing il y a quelques jours. Et donc, on distingue aussi des exposés donc, à connotation plus intelligence artificielle. Voilà, donc ça va faire un certain nombre d'équilibres. Avec donc, après la pause, donc on aura une pause pour ceux ici présents qui se passera donc au CINES, juste à côté. Et juste après, donc, vous aurez un exposé un peu prospectif d'HPE. Ad Astra, c'est une technologie HPE créée donc AMD, qui nous retracera quelques éléments importants de l'évolution des supercalculateurs dans cette période. Voilà, donc ça sera à 13 h, juste après la pause. Voilà, donc je ne vais pas être plus long. Le CINES, c'est 3 missions d'intérêt national. L'hébergement d'infrastructures de calcul numérique au sens large. Ensuite, une mission d'archivage pérenne des données. Donc, on a eu enfin la certification VITAM, qui est la norme actuellement nationale, pareil, il y a quelques jours. Et donc, c'est important pour le dépôt des archives. Les archives, c'est aussi les données. Et on voit bien que ce couplage calcul et données est stratégiquement très important. Et bien sûr, la mission historique depuis 45 ans. Donc, le CINES développe des moyens de calcul intensifs. Et aujourd'hui, donc, avec GENCI, on a eu, je dirais, l'opportunité et la chance d'avoir eu ce calculateur ad astra. Et donc, dans un contexte où on voit bien que les machines évoluent très rapidement en fonction des composants, c'est-à-dire des partitions, ça va très, très vite. Et on espère, en tout cas, au niveau national, avec les 2 autres centres TGCC Idriss, répondre au mieux aux attentes qui sont de plus en plus fortes sur les moyens de calcul. Et tout ça, c'est une organisation. Non seulement il y a le choix des machines, mais il y a aussi la répartition des heures de calcul. Voilà, donc je voudrais vous souhaiter la bienvenue. Et évidemment, chacun est spécialiste son domaine. Donc, quand on voit le programme, il y a à la fois des exposés académiques, industriels. Donc, ce sera très intéressant. Mais vous en convenez, chacun peut être spécialiste de tous les sujets. Donc, c'est aussi la pédagogie et en même temps le retour d'expérience. On est là pour des retours d'expérience et pour améliorer les choses. Donc, ce qui nous intéresse, c'est bien sûr ce que vous avez fait, puisque c'est important pour nous, et notamment pour les tutelles, de savoir finalement l'usage des supercalculateurs. Et donc, en même temps, donc, quelles sont les marges de progrès ou quelles sont vos attentes, etc., etc. Donc, ça sera animé par des responsables de session. Et donc, je donne la parole à Philippe, donc pour GENCI. Merci.
Merci beaucoup, Michel, pour cette introduction vraiment complète. Je pense que ça va me simplifier la tâche pour la suite. Bonjour à toutes et à tous. Alors, effectivement, on parlait de bilan carbone il y a quelques instants. Mais enfin, moi, j'ai eu le plaisir de me déplacer depuis Paris parce que je pense que pour les rapports humains, rien ne vaut le présentiel. Et de temps en temps, il faut savoir quand même trouver un équilibre pour venir à la rencontre des équipes. Alors, la journée d'aujourd'hui, c'est le fruit d'une collaboration entre GENCI et le CINES depuis de très nombreuses années. Dans l'émission de GENCI, c'est l'implémentation du HPC, hein, c'était historique depuis 2007. Depuis 2018, c'était l'implémentation du plan national IA. Depuis 2021, c'est l'implémentation du plan national quantique. Maintenant, c'est l'ensemble, c'est le tout. Là, aujourd'hui, on se retrouve autour plus particulièrement des grands challenges autour des aspects accélérés. Alors, il y a eu une présentation il y a quelques semaines, là, au mois d'octobre, sur les tests et les challenges scalaires. Là, on se retrouve au niveau de l'accéléré. Alors, c'était vraiment accéléré parce que je vais surtout distribuer des remerciements aux équipes techniques et aux communications là, du CINES hein, pour tout ce qui s'est préparé pour cette journée. Et dans les dernières semaines, plus particulièrement, je remercie à GENCI le directeur technique Stéphane Requena, la chargée de communication Annabelle Truong et également Eric, qui a, au niveau de la responsabilité de la cellule de veille, a suivi tous ces grands challenges avec intérêt et passion, parce qu'ils ont vraiment fait du boulot. Alors, à quelques jours près, vous auriez eu le PDF des grands challenges accélérés. Celui des scalaires est sorti la semaine dernière. Vous avez peut-être vu ça pour ceux qui sont connectés sur le site. Bon, quelques heures de patience supplémentaires et le PDF accéléré va sortir en même temps. En tous les cas, c'est vraiment un très beau boulot. Merci à toutes les équipes. Et puis, ravi aujourd'hui, moi, de rencontrer les scientifiques qui utilisent nos machines, parce que ça, je suis à l'écoute au moment de la poste pour savoir qu'est-ce qu'il vous faut pour le futur. Hein, parce que, bien évidemment, on sait bien qu'on n'en a jamais assez. Très bonne journée de science à tout le monde.
Merci. Donc, on va démarrer. Alors, moi, j'avais oublié, effectivement, il y a beaucoup de personnes impliquées. Donc, on a ici présent le département de calcul intensif, hein, en particulier avec Gabriel et Joanne. On a la DSI avec Marie Galès. Et, comme on dit, Atlas but not least, donc Anaïs Rambier en haut. Donc, Anaïs, que vous avez eu en contact, donc tu peux lever la main. Donc, Anaïs Rambier, donc, qui gère tout ce qui est ici, j'allais dire, la logistique et donc tout ce qui est communication. Merci Anaïs et à tous les services impliqués. Et donc, on ne va pas perdre plus de temps. Et donc, Eric va couper son téléphone et va venir me rejoindre pour présenter donc, cette première session. Donc, on va avoir une alternance de collègues de GENCI et de CINES et du CINES pour animer. Donc, on va démarrer. Tout est prêt. Normalement, les diapositives sont téléchargées. On va essayer d'être le plus fluide possible. Et donc, Eric, je te laisse le micro donc, pour gérer au mieux le temps. Donc, déjà, on t'a fait gagner 10 minutes.
Merci beaucoup, Michel. Bon, j'étais au téléphone pour la bonne cause avec Stéphane Requena, je tiens à le préciser. Bonjour Stéphane, bonjour à tous. Pour la première session, oui, est-ce que vous m'entendez un petit peu mieux? Voilà. OK, c'est vrai qu'on est enregistré. Première session, il s'agit de simulation à grande échelle du dynamo-convective stellaire avec une particularité, enfin qui m'intéresse particulièrement, c'est un traitement de données in situ qui est une des clés pour le passage à l'échelle d'application. Donc, je laisse la parole à Rémi Bourgeois du CEA qui va nous faire cette présentation. C'est toi. Tu parles dans le micro. Ouais, et occupé, c'est possible. À la fin, j'ai une vidéo, c'est bon. Je l'avais envoyé. Ok. Voilà. C'est bon. Merci.
C'est bon? Ouais. So I'll be speaking in English today, if that's okay for everyone. So it's an honor to be here today for the restitution of the Grand Challenges on the Adastra machine. And today I will present a pre-exascale IO-intensive simulation of turbulent convective dynamo powered by COCOS, PDA, and DESA. So I'm Rémi Bourgeois. I'm a research engineer at Direction des Énergies at CEA, but I did this work when I was a PhD student at the Maison de la Simulation, along with my team. So I will start with a motivational physics example, which is the magnetic field of the AP and BP type stars. So let's start with this physics puzzle. So what are AP and BP stars? These type of stars are called chemically peculiar because they present a overabundance of metals such as strontium. They have more heavy metals than other stars in their atmosphere. And they also present a very strong magnetic field, which is difficult to explain. Researchers are not sure of why there is such a strong magnetic field in these stars. And there are two main theories for the strength of this magnetic field. The first one is the fossil field theory, which means that the magnetic field of these stars would be a remain of the interstellar medium field. But then we're not sure why this magnetic field would be so stable. The second theory is that this magnetic field could be maintained by the dynamo effect in the core. So the core is rotating, it's magnetized, and so by dynamo effect, the magnetic field would be maintained. But it seems that the geometry of this magnetic field indicates otherwise. So these two theories are not very satisfying. And so we have a proposition that maybe this magnetic field could be maintained by convective dynamo in the atmosphere. So in stars, in some stars, you have convection in the convective zone, so the rolls. And since stars are made of plasma, of charged material, these charges are rotating and this generates a magnetic field. So we think that maybe this magnetic field could be maintained by this rotation in the atmosphere of the star. And so to describe such a system, you need quite rich physics, right? So you need your fluid, gravity, because convection is driven by gravity. You need variation in temperature. So the most known version of convection is thermal convection. So you have hot air that rises and cold air that goes down, right? You also have thermal sources, such as the conduction of the heat, the contact with the radiative zone of the star. But another element that goes into account is composition, right? Because we have this variation of heavy elements in these AP and BP stars. So the variation in composition impacts convection too. And we have composition sources, such as the diffusion of these heavy elements. And lastly, we have the magnetic field of the star and the magnetic sources that comes along with it. And so if you mix all these effects together, that's what I did in my PhD. By mixing all these effects, we discovered a new type of convection, a new type of potential convective dynamo that could maybe explain the magnetic field of AP and BP stars. So that's all in my PhD. And the Ad Astra supercomputer allowed us to test our new framework, our new theory at a very high resolution. Now we'll do a very short introduction to supercomputers, GPU, and the I/O bottleneck. So here on the left, I show the evolution of the computational capacity of the fastest supercomputer in the last 30 years. So we can see that since the y-axis is logarithmic, this growth is exponential. So it's been growing exponentially for the last 30 years. But on the right-hand side, I show the ratio of the I/O bandwidth, so the I/O capacity of supercomputers, divided by the computing power of the supercomputers. And you can see that this ratio is decreasing quite exponentially. So there is an increasing gap between the compute performances and the I/O performances of supercomputer. We are computing faster and faster, but we're not able to write on disk quite as fast, right? And so this ratio has been divided by 10 over the last 10 years, typically on the last 3 supercomputers. And so software efforts have to be made in order to mitigate this gap and to be able to exploit large-scale simulation. Because if I do super large-scale simulation, but I'm blinded by the amount of data I have to process, my simulation is useless, right? And so GPUs, so I showed the growth of the computational capacity of supercomputers, and it's been enabled in the most recent years by the use of GPUs, graphic processing units. So here we have the AMD MI250X, which are the ones that are in Ad Astra and that I used for the Grand Challenge. We also have the more recent MI300. We also have the newer partition in Ad Astra with these APUs. And then the NVIDIA H100, right? And so a supercomputer, as you all know, is essentially a large amount of GPUs put together and with means for them to talk to each other. And so usually for large-scale simulation, the strategy we use is domain decomposition. So my simulation is convection in a box, essentially. The box is represented here. And you essentially subdivide this box into subdomain and you attach each subdomain to one GPU. And this way you can leverage your whole supercomputer to do a large-scale simulation. And so software effort has been made to be able to use efficiently these GPUs. So the vendors have developed their backends. So AMD have developed HIP that allows you to code on 4 AMD GPUs. NVIDIA has developed CUDA to leverage NVIDIA's GPUs. Other software have to be used to scale your code to full machine. So in our case, we used MPI that allows you to have your GPUs talking to each other on the software level. And lastly, portability performance libraries have been developed, such as Cocos and SQL. And these libraries allows you to write only one code that will run on several GPUs and CPUs. So for example, the code we used uses Cocos, and we just wrote one version of the code, and we can compile it on NVIDIA GPUs and AMD GPUs. So it's a lot easier to maintain. Okay, so I'll now present very quickly the code that we use. So the code is named ARC2MHD. ARC stands for All-Regime Cocos, and MHD for Magnetohydrodynamics. It's a fork of the work of Thomas Padiolo in 2019 that was done for pure hydrodynamics. It's a C++ multi-CPU, GPU, finite volume MHD code for 3D Cartesian meshes. And it uses a fully explicit and robust numerical scheme, the one that we developed with my PhD advisor in 2024 for MHD and thermocompositional flow. And the code can be compiled for both CPUs and GPUs, thanks to Cocos, right? The kernels are scaled to many nodes thanks to the MPI library. And lastly, we handle the I/O of our simulation with 2 libraries. The first one is PDI, so the Parallel Data Interface, the work of Julien Bigot. And the second one is DESA. It's a Dask-enabled in situ analytics, and that's the work of Amal Gerouchi. So here we have some performances of our code. So our code uses double precision, FP64, and it's memory bound. So to give you some ideas of what's going on. So we have the performances. So higher is better. This is the amount of cell update per second that we can do on several GPUs. So we have the NVIDIA V100, A100, and H100. We can see, and then the MI250X that we use for the Grand Challenge, and the more recent MI300A that are in Adastra. You can see that between each generation of GPUs, there is an essentially 30 to 40% increase in the computational capacity. Then we also did a weak scaling experiment on Adastra. So weak scaling is essentially if I use twice as more GPUs, am I going twice as fast? Is my system stable and my code stable? And the answer is yes. So here we have the amount of GPUs that we use, and here we have the performance of the code, and we can see that the weak scaling is linear, near ideal. So Adastra was able to scale very, very well our code. But the raw performances are not the whole story. We also need to look at the performances per watt. So I scaled this result by the top consumption of the GPUs, and you can see that between the 2 generations of AMD GPUs, between the MI250X and MI300A, there is a huge improvement in energy efficiency, and it's now very near to the NVIDIA GPUs A100 and H100. And we can discuss this result later because there is a lot of caveats. So now I'll present the simulation, our I/O concerns, and PDI and DESA. So these are some stats about our simulation. So it's convection in a cube. This cube is divided in 4,096 cells in each direction. So this amounts to 70 billion cells. There are non-variables per cells, and this whole domain is distributed onto 1,024 AMD GPUs, which amounts to 2,048 MPI processes. This cost 130K hours of computing power that lasted 60 hours in real life, right? The memory it required was 40 terabytes to do the computation, sorry. And the weight of one output is 5 terabytes. And that's the crux of the issue, right? Because 5 terabytes per output is a lot of data. So how do you look at so much data? That's a problem of exascale computing. Because with outputs of 5 terabytes, you cannot save your output at high frequency and then look back at it later. You don't have enough storage and it will take forever to write. So we need to perform reduction during the simulation, so global averages, slices, and reduction along axis. And to do so, we use the PDI library, which allows you to couple your MPI code, so your code that use a lot of nodes. It allows you to couple your code to high performance IO libraries such as VDK or HDF5. And we also did in situ analytics of the solution using DESA. And DESA allows you to run analytics on your simulation data during the simulation, not afterwards, right? So in situ. And these analytics use separate computational resources from your simulation. And we believe that these type of tools are going to be essential in the exascale era. So our strategy is the following. We started the simulation at a very low resolution, 256 cube, and we progressively increased the resolution by doing upscalings. And the question is, when do you want to do the upscaling? And the answer is when the flow has converged. And if you know a bit of fluid dynamics, you might know that you can check that your flow has converged by checking the kinetic power spectrum of the simulation. So essentially, what's the state of the turbulence in your simulation? And this computation, it's typically done on a slice of your simulation. So what we did is we take just a middle slice of our simulation and compute the power spectrum on this slice. This simulation, it does not scale to the full machine. We are just looking at a slice. So when we do this computation, all the GPUs except a few are idle. So we want to do this computation on separate computational resources to not lose time on the main simulation. And DESA allowed us to do so. So the results now. First, DESA works, right? So in situ analytics, here we have the kinetic power spectrum. So two plots. The black one is one done on the post-treatment, so the 5 terabytes output, and we just do the power spectrum. And then we have the one done in situ by DESA during the simulation. And we can see that both coincide. So the scheme worked, and Adastra was able to restitute this good result. So this FFT, we believe that it's a stepping stone for safe piloted simulation. What we wish to do in future work would be to decide to detect when this kinetic power spectrum has converged, and then send back a signal to the code that would trigger the upscaling without us doing by hand. The second result is the dynamo effect. So here, during the simulation, we did global averages of the kinetic energy and the magnetic energy. So at the very start, so the black line, the dense one, is the kinetic energy. So as we start the simulation, convection starts, and so the rolls are appearing, and these rolls are associated with the kinetic energy because matter is moving, right? And as the rolls are installed, they now generate magnetic energy, which is the dotted line. And so we can see that there is a convective dynamo effect because magnetic energy is generated from convection. Lastly, kind of convergence study or non-convergence study, actually. Here we have the resolution. So we increase the resolution from 256 cube to 512 and then up all the way to 496. And we can see that as we increase the resolution, the magnetic energy grew as well. And that's something that we expect from our theory, since we don't use any diffusion or resistivity. So this result kind of validates our theory among other results. Lastly, I would like to show a video of the simulation. It works, sorry, no spoiler. So this video is a vertical slice of the density perturbation. So here, you have to imagine simulation in the cube, right, that go through the wall. And light color corresponds to under density, so light fluid, light plasma, and dark color corresponds to heavy density, so heavy plasma. Here it is. So Adastra allowed us to have this very high resolution video. It seems that matter is coming through, so in and out of the simulation, and that's the case because we are just looking at a slice of the simulation. And this slice extraction was done thanks to PDI. Because you can do high frequency output of slice, that's not an issue because each slice is not 5 terabytes. And yes, that's it for me. So I want to thank the CINES for selecting our project and allowing us the computational resources and all their help during this project. And this is a picture from the Grand Challenge Hackathon back in December 2022. So thank you. Any question?
Many thanks for this first talk. Always difficult to start the day. Can you come back to one of your last slide in which you explained that the magnetic energy is increasing due to the numerical scheme? I didn't grasp it completely. If it is easy to say. If not, we will discuss during the pause. Okay, so we discuss during the pause.
So essentially, we're doing ideal magneto-hydrodynamics. So just like pure hydrodynamics with no like diffusion process, your solution doesn't converge, right? Because as you reduce diffusion, turbulence increases. And in our theoretical framework from convection, we saw that if you reduce diffusion resistivity, you will increase, you have a more dynamo, more energy. So as we increase resolution, we decrease diffusion, and therefore we have more magnetic energy. That's the idea, essentially. That's an indirect result, yeah.
Thank you for the great talk. I do have a question regarding the measurements or the values you showed regarding the energy consumption or the cells update per watts. Are those measurements or just projections on the values you have?
I did some of these tests a long time ago, right? The most recent are on the MI300A, and what I took is the peak TDP, right, of TDP and divided. But yeah, I'm aware it's not the ideal way to do that, but still, it seems to have a lot of progress in the efficiency.
So it's a raw measure, not actual measurement at the time of the simulation. But it's a start. Okay, we understood. Okay, understood. Another question?
Thank you very much. Just looking at the ratio of your output size and the total size of the output, it seems that you have only 8 output for the whole simulation. So I was wondering what is your strategy to investigate the processes that played in the star just with 8 output? Do you have already like set up some diagnostic along the simulation to see these processes going on?
Yeah. You mean that there are only 8 outputs? What do you mean? Okay, no. So you refer to my slide where I see the total memory required. So what I meant there is that the numerical scheme requires 40 terabytes of RAM in the GPUs to run, but the solution weighs 5 terabytes. So we made more than 8 outputs, right? But this is just the memory that your math requires, essentially, the program requires. But the strategy was to do a lot of like a high frequency of low-sized outputs. That was the strategy. If that answers your question.
Another question? I have one. Well, if you can answer, it's okay. But well, we are trying to design and to propose the best machine for your simulation. Mm-hmm. And I would like to know when you have performed some data in situ processing, are you expecting more in performance in which area would you recommend us to insist or to stress on? Less latency, more throughput, whatever.
So for the type of actually for the type of computation that we're doing, I think the most crucial is the memory transfer, right? Because most of the cost of this computation,
Yes.
I would assume it's in sending the data to the data node that does the in situ analytics.
Okay.
But then the strategy to offload this work out of the computational nodes saves us the issue, because then the data is doing our work and the simulation is still going. So that's this transfer essentially.
Okay.
So honestly, it was perfect as it is. But you might want to ask this question to the people who are developing data.
We will do.
Yeah, I can definitely give you their contact.
Yes. Yes. So thank you. If there are not any question, I would like to thank you again for this very. It was wonderful at the end of the movie.
Thank you.
And the content also. Thank you.
Thank you so much.
If I'm not mistaken, next speaker is not there. So it's Florent Bartoccioni from Valeo. It's about detecting users on the road by analyzing data from lidars and captors, and it's about autonomous driving. I did it in English. Sorry for that.
Yes, it will be.
So the floor is yours. Does it work?
Should be now. You seeing my screen?
Yes, we can.
Okay, perfect. Okay, so hello everyone. I'm Florent Bartoccioni, and so I'm the principal investigator of the World Model Initiative at Valeo AI. And so I think there was a small confusion. I will not talk about LiDAR. I will talk about, I think it's for maybe the next speaker, Spiros. I will talk about world models. And so I will present what is a world model and why we need one, and the result of our experiments during the Ad-Astra Grand Challenge. So I will begin by shortly present what is Valeo AI. So Valeo is a global automotive suppliers that design, manufactures, and sells a wide range of products and systems for vehicles, including lighting, powertrain systems, thermal systems, and autonomous driving technologies. And Valeo AI is a research lab of around 30 people within Valeo that is dedicated to open research. So all our work is openly released on GitHub. We publish to scientific conferences, and we work continuously with multiple academic partners across France and Europe. So moving to the autonomous driving part, I would like to highlight that there is a whole spectrum of automation for driving. So driving assistance systems like auto braking or lane departure warning, for example, are already and significantly saving lives. So of course, the ultimate goal is to be able to do the full self-driving, to have full self-driving capabilities. But to reach this point, there are still a lot of steps that we need to get right. So let's dive in. So a core need to driving is to represent the environment. In particular, you want to recognize and localize road users. You also want to detect and also localize road directive like traffic lights or signs. And more generally, you want to extract the geometry, the dynamic, and the semantic of the scene. So in the past decades, a prevalent approach was to explicitly represent everything in the scene. So this requires a lot of human efforts, as we first have to annotate what we think is everything as important in the scene. The issue with this approach is that what is not defined does not exist. If you have not annotated something, you can't detect it. This is a major impediment to scalability, as the world is unpredictable and ever-changing. people do not always, and if not often, behave as expected, and the infrastructure does not always meet public standards. So that's where a world model comes into play. And I will now go into details, but the high-level idea is to be able to learn at very large scale without needing any human annotation. So first, I will draw a parallel with GPT, because at the core, we use the same principles. So how does GPT works? It relies on the principle of next word prediction. If I say veni, vedi, certainly you will think of vici. And you infer the most likely next word given the past context. And that's basically how GPT learns. We mask the next word and make the network predict it. So this is entirely self-supervised. The one through the supervisory signal is trivial to obtain. And this way, it learns a very powerful representation about the relationship between words and their context. This representation can then be used for multiple applications, such as chat, mail answering, or document analysis, for example. And for driving data, we relied on the same principles. As the difference that we now have images and action, because we would like to know how the world evolves given how we act. So if the model successfully solved this task, that is to predict the future observation of the world given the past, it means that the model extracted a lot of correspondences and useful correlation about the world. That pixels that looks like cars move a certain way, and that pedestrians move another way. So that means that it should have learned a lot about the geometry, the dynamic, and the semantic of the world. So we actually trained a world model on some data, and we'll now show some results. So we have actually two models. So it's the same model, it's just that we have a small version at 20 million parameters, and another bigger one at 500 million parameters. On the left column, what you see is the context that we give to our model. We give at least 3 frames so that the model can extract the initial dynamic of the scene, the speed and accelerations. Here we see a car starts to appear and driving towards our right. We also notice a white and a gray car in the background. Okay, so now let's look at the world model prediction. And did it predict the future accurately? So, well, it did. So what do we have now? On the left are real images. So this is not the context anymore. The model is not has never saw those images. This is for you to check if the model correctly predicted the future. It is the ground truth. It is what we actually want to predict. And on the right, you have the generation for their respective models. So several things to observe. First, the general structure of the future is correctly predicted. Second, as we increase the model in size, the prediction gets more accurate, both visually, geometrically speaking. And a detail to notice here is the white car in the background that we saw earlier here gets occluded on the second frame. We see it here, then it's occluded and it reappears here. You see that the small model here is unable to extract this fact, and the white car essentially disappears after it gets occluded. So you see that as we scale the model, we have some capabilities of occlusion understanding that appears. So, okay, so these are other images as the video continues. So, okay, now we can generate nice images, but so what? So bothered by this question, we started to open the hood of our model and analyze what is actually learned when you look at the representation of the model. So we looked at the feature map of our models. So the dimension is in the thousands. So we projected the features with PCA on 3 components, and mapped the eigenvalues to RGB channels. So what we can observe here is that the features start to be semantically clustered. We can easily distinguish in blue here the pedestrians here. We can also notice the crosswalk have different features, the road, the cars, the road marking, the background, even the trees have different, actual different features. So by simply predicting the future frames, by solving this task, the model learns that pixels looking like cars move a certain way and pixels looking like pedestrian moved in another. So for now, unfortunately, I only have qualitative analysis to show you, as this is still a work in progress. Yeah, so this is some of the detail of the architecture. I will skip it, and maybe if you have questions. So what I showed you was done entirely on Adastra and only on about 90 hours of videos. And we scaled the model only up to 500 million parameters, which is already big, but compared to current foundation model, like what we see in LLMs that are in the billion scales, it's still small in comparison. So what's next is that we want first to, because now, okay, we have a world model, we are starting to study what is learned, we are able to generate nice images, but what we want to do is actually to drive with it. So on that, we are able to predict. What we want next to is to evaluate this model, first to fine-tune it for planning and control. As we are able to predict the future state of the world, we can explore this future and predict ideally the best sequence of action to take. So that's for future work. And second part of our future work is to scale, simply to learn on more data. And it appears that on internet you have entire YouTube channels dedicated to driving. So you have people putting a 4K camera on the hood of their vehicle and drive in really around the world. And the videos are of very good quality. So this provides us with an opportunity to actually learn from internet data, like LLMs did, at an unmatched level of variation. That in terms of driving data, it's called OpenDV YouTube. It's almost 2,000 hours of driving data. So it is unfortunately uncalibrated, but still we think that we can learn a lot using this world modeling approach just by looking at this, just by learning on these videos. We have also employed two important methods to scale. First one is, we not go into detail, and we just give you the high level principle of this method. But first, it's called the maximal update parameterization. And the idea here is to parameterize your network in such a way that the activation are normalized layer after layer. So if you take a network and use the standard parameterization from PyTorch, if you look at the activation of your network, so it explodes. So here, what you see in this line, each colored line corresponds to the output of one of the output of your model. So you have in your model you have multiple layers, you have multiple activation, feature map, and what you see here, each colored line corresponds to one of the layer, and you do the absolute average of those output on your feature map. On the axis here, it is the size of your model. And on the y-axis, it is the, this mean average. And T1, T2, T3, T4 is the number of backpropagation steps that we do on this network. And as you can see, as you scale your network from a small size to a bigger size, you see that it explodes, and this behavior continue as you train your network. As you see, as after several gradient steps, we really explode in terms of activation scale. Whereas with this parameterization, and I will let you take a look at the paper, is that you see that our activation stay stable across different size of model. So why this is a good thing? The nice thing is that this allows us to have a very efficient hyperparameter search, in the sense that here you see this is the loss, the loss of across different learning rates for different model size, and you see that as you scale the model, the best learning rate shifts. So each time you scale your model, you have to find again the best hyperparameters. Whereas here with this parameterization, everything is aligned. You have a nice optimum basin that emerge. So the nice thing is that with this parameterization, you can do your hyperparameter grid search on a small scale model very fast in parallel, and then you do a zero-shot transfer towards the bigger model, to the 1 billion model. You really zero-shot transfer your hyperparameter. And so that's what we are currently using. We have validated it, and it works actually very well. So the result will be for the next presentation. So thank you for your attention.
Any question in the audience?
Thank you very much for your talk. Do you mind saying a few words to what the model architecture looks like, actually?
So the model is in two parts. For text, okay, I will go on this slide. For text, what you do is you usually have what is called a tokenizer. Roughly speaking, you are converting text into numbers, into discrete numbers. And your architecture, typically something similar to a GPT, will predict the next number corresponding to the next word. And that is the decoder that will do this final conversion. With images, it's a bit complicated. We use the same principle. We convert images to these discrete numbers. We still are using a GPT, so it predicts the next number corresponding to the next frames, and the decoder convert this predicted number into the final image. So unfortunately, I don't think I will have the time to go into the details, but the architecture is called a VQ-VAE. The VQ again here is the specific instance of this kind of architecture, but it allows us to convert images into a sequence of number. This sequence of number is then given to a GPT, which is really a stack of causal attention layer. And that is it. That is really the architecture.
Thank you.
Thank you. Another question? I might have one. You presented a way of optimizing the use of resources by scaling the model. Can you develop a little on what is your ideal machine in terms of size and power? If I understand well, and it's a good news, it's not the Mr. Musk machine that you need. So can you express something about what is the ideal size of the machine you should need?
The ideal size of the machine, well, it will certainly depends on the scale of your data. Right now, I think one of the main issue that we have was first the number of inodes. At this scale, you have to the thing that will be the most complicated, I mean, technically speaking, is to handle this large amount of data, to handle the I/O, to have a good I/O performance so that your GPU does not starve, that you are not using all of the bandwidth of the NFS. So at this point, you have to use things like sharding and web data set, for example. I think another bottleneck may be the RAM, the memory available per GPU. You have to have a good amount of RAM per GPU. For now, I think in terms of GPU at this scale, it was enough for us because even though we have a lot of data, it's still not enough, at least in terms of driving data. It's maybe not the case if you use internet data like all kind of video, but only for driving data, we do not have yet enough data to reach, let's say, the capacity that Ad Astra had given us during the Grand Challenge.
Okay,
Purely in terms of GPUs.
Okay, thank you. Maybe we'll come back to you and ask some question when it will come to providing a good architecture for next machine we'll put in production. Thank you.
You're welcome.
Are there any other question? If not, it seems not, I would like to thank you again.
My pleasure.
Bye. Next speaker is supposed also to be online, and I will switch to French, sauf si quelqu'un a une objection à propos de cela. Alors, le sujet, c'est images, son, langage, et un seul modèle pour tous. Alors, c'est pas du Tolkien, c'est Mathieu Corde, Sorbonne, Université Pierre et Marie Curie, qui va nous présenter un développement d'approche multimodale. Mathieu.
Yeah, it's actually me who presented instead of Matthew. It's Mustafa. I'm his PhD student. Yeah.
Welcome.
If that's okay for him. So should I share my slides, I guess? Maybe I'll present it like this. I think that there's an issue with the connection. But yeah, or let me try. Yep. I guess now you can see it. That's good. Okay, so hello everyone, I'm Mustafa, and I'm going to present a project that we published 1 year ago. It's quite old now, given the recent development of recent foundation models, and it's in collaboration with Alex, Corentin, and Mathieu at Sorbonne University. So before diving into the details, I'm going to present just an overview about multimodal models in general. So what we are interested in is this kind of models that can take multiple modalities. By modalities, I mean, for example, we consider text as a modality, image as another modality, video and audio. and can produce text. So the kind of tasks that we are interested in are, for example, question answering, where we give the model an image and an answer, and we expect the model to answer the question based on the information seen in the image. Yeah, and we can see question answer. We can do question answering, or for example, detection, where we can answer the model. We can ask the model to provide an answer based on particular region in the image, as we can see in the first example. So these kinds of models have now a long history. They started a long time ago, but by training single models, relatively small models on particular task. So if the interest is to have or to solve a particular task, so you have relatively few 100 million parameters models that is trained on target data set, and that's it. So usually everything was small, the model is small, the data set is small, and the training is not is very short. And then after a couple of years, we started to see multitask models, where we have slightly bigger models that are trained on many tasks at the same time. So here the models are slightly larger, the training is obviously longer, and the data sets, because they are a mixture of different data sets, obviously they are slightly bigger. And it's up until recently that we started to see these giant models that are unified, in the sense that we have a single model that can process many tasks at the same time, and maybe many modalities at the same time. So we have giant models in the order of a couple of billions to hundreds of billions of parameters. We have massive data sets in terms of, in the order of a trillion of tokens, for example. The training is very long, and it's usually also very challenging. So what we are interested in this project is actually how we do or how we build unified models, but at a very small scale. So how we can be more efficient while targeting multiple modalities at the same time. And this is the core of the project. So before going into the research details, so this is like an overview about the technical work that we conducted at the cluster, the cluster. It's basically distributed into two main parts. We have the pre-training, which takes most of the resources, and we have post-training. In the pre-training, we iterated on different aspects, so that mainly the data sets. So these data sets are in the order of a couple of tens or a couple of terabytes, up to tens of terabytes of image, video, and audio and text. The training usually, so our final model is trained on 128 GPUs with 64 gigabytes each. And usually it takes between 2 and 4 days for each training to finish. It depends on the data set that we train on. And usually the evaluation takes a couple of hours, at max 1 day, usually on 1 month. For the post-training, this is the stage where we do fine-tuning, where we specialize the model to do multiple tasks. Usually it takes 2 days on 2 nodes on same GPUs. Yeah, good. So this is what we propose. It's a model we call nouveaux. It's a single model with very light projectors that can project all modalities to a unified space, which is the token space. And we produce also tokens. So it's sequence to sequence model. So we have sequence of tokens as input, sequence of token as output. And as you can see, we can pass video and questions about these videos. We can pass images and questions about these images. We can ask to describe the images. And as I will show later, we can also pass audio and similarly questions, instructions about the input audio. And on the output side, we have we can produce text, so the answer to the questions, but also we can produce detection. And we have some experiments where we can produce actually images by plugging a image decoder in this case. So the second aspect is unification. So the unification is on multiple axes. So first, the architecture. As I said, it's single architecture, one architecture that is used across all tasks, in the sense that we don't have like specific heads per task or specific module, big modules per modality. You only have one transformer. I will explain the architecture later. In the middle, and you have very lightweight projectors that project the different modalities to tokens. So we have the same architectures. Input, output are formal or are represented as tokens in unified way. The vocabulary is also shared. So we have the vocabulary includes the text tokens, the discrete image tokens, and the detection tokens, which are actually the position in the image in terms of pixels. All tasks are also formatted in a unified way where it depends. It's specified by the prompt. So the model behave differently when we see different prompts. And of course, everything is trained with single objective, which is next token prediction. The last aspect is the efficiency. So we know that this kind of models, so now you see GPT-4V, Gemini. We believe that these models follow similar architecture in the sense that they are unified. It's a big giant model that can process multiple modalities. But we know that they are giant models, very big. And here, what we are interested in is having something very small. So the efficiency is in terms of model size, it's 250 million parameters and is trained on relatively small data sets. So it's compared to other similar models, of course. So it's 26 million samples of image, video, and text. Yeah. In terms of architecture, so it's transformer. In this case, it's an encoder decoder, and it's initialized from a pre-trained language model. So we initialize from BART, it's 150 million parameter models. It's also quite old now, but still works good. For the lightweight projectors, it's actually CINES. So for example, we don't take all the encoder. For example, we take, for example, ResNets or image trained for classification, for example, on ImageNet or for audio classification or video classification. And we take part of this network to obtain the final tokens. So in the encoder, we have attention. And this attention is bidirectional in the sense that each token can see all the other tokens, not only the previous ones. While in the decoder, so when all these tokens are projected inside the decoder through cross attention, so here each token can see only the previous ones. So here it's causal. The attention is triangular. And the goal here is to generate the answer, actually. So the answer could be text. It's always tokens, could be text or detection or image, discrete image tokens. We trained the model on a mixture of image, video, text tasks. These spans tasks like captioning and question answering. Captioning, it's image description. So the data sets is image and description of the image or video and description about the video. Question answering, image question answering, and video question answering. Also, we have some grounding tasks. So the grounding is where we ask the model to provide bounding box, for example, about an object inside the image. So this is the pre-training set. The downstream tasks are actually also similar to the pre-training, where for each task we fine-tune to get specialized model on these tasks. So we have, again, image captioning, PQA detection, audio captioning, video captioning, and yeah, we should have also image generation. Yeah. So now the main point is how we can train unified model to be small and good and powerful on many tasks, many modalities. And we actually propose it's kind of tricks. So we are not like the first one to propose these concepts, but we adapt them and somehow to this context. So the first thing that we propose is what we call multimodal curriculum learning. And the basic idea is instead of training on all modalities at the same time, so instead of starting from scratch and training on text, image, and video, so we do it incrementally. We start by training on text. Then we add, in the second stage, we add images. So now we train on image plus text. And then we add the video, and then we train on text, image, and video, and so on. So this is a general paradigm to train for N modalities. And what we found is that it is actually efficient and leads to comparable performance. So what I'm showing here is the first line is the one-stage training, the baseline. The second is the curriculum learning. And we report the training time and the batch size. And what we can see is if you look at the all scores, they are very close. They are comparable. Sometimes the curriculum learning is slightly better. But in terms of memory, we are saving 25% of the training memory, and the training is actually around 20 times faster compared to the first one. And we are getting the same performance. So this is the first thing that we propose. The second thing is the multitask aspect. So here we have design choice. So either we train on all tasks at the same time, or we train on single task. And what we are showing here is actually there is benefits of training on multitasks because it's kind of different tasks can help each other. So what is important here is the numbers highlighted in red and blue. So for example, if you look at the numbers in red, so we have actually the same data set size. It's around 20 million samples, but one is trained on single task and the other is trained on multitask. And this single task is actually image captioning. So what's interesting here is if you look at the COCO, which is an image captioning downstream task, actually the one trained on multitask, so on image captioning, VQA, and the grounding is also better on the image captioning score. So this gives us an idea that this is another source of efficiency in the sense that we can get, for the same amount of samples, significantly higher score by just training on different tasks at the same time. Yeah, so here we have also another design choice, which is when we do multitask training, because the sizes of the data sets are significantly different. So here we either do balancing in the sense that each batch contains the same number of samples for different tasks, or it's proportional to the data set size. Sometimes you have like many samples from particular tasks and very small number of samples for other tasks. And here we are comparing the two. For example, if we simply look at the last one, it's the same model trained on the same data sets, but we either do task balancing or not. And as you can see, is if we do task balancing, we actually get better performance. So now we have the main recipe to do the training. We start by doing the multimodal curriculum learning in terms of modality. We add each modality at a time. And then, but within each modality, because each modality has many tasks, we train on many tasks in a balanced multitask way. So now the main results. The objective, again, is not to get the state-of-the-art results, but it's rather to show that with very small model that is unified, that can tackle many modalities, we can get comparable scores to other models that are specialized. So all the models that are not highlighted are not unified. The ones that are highlighted are unified, but can do only two modalities. So they can do, for example, in the first case, video text task or image text task, where our model can do image text task, video text tasks, and then at the end, I will show you some audio tasks as well. And as you can see, so the scores are comparable while being unified, multimodal, and efficient. So here what we are interested in is if our model can generalize to new modalities. So in the pre-training set, we have only image, video, and text tasks. But here we are evaluating on audio tasks. So what we do is we take the same model, we plug a lightweight audio encoder, and we fine-tune it on new tasks. And what is interesting here is, so for audio capture, we have enough data. Actually, our model is significantly better than others that are specialized for these audio captioning in this case. And it's comparable on other data set that is very small compared to the first one. But it gives us the same message that our model has very good generalization ability to new modalities. Yeah, so now for post-training, we propose something a little bit novel. So it's about multimodal model merging. And the idea is, given or the assumption is, now we have many fine-tuned models. Can we leverage them in somehow? So the basic idea is you have two different fine-tuned models. You can simply average their weights because in our case, it's the same architecture. And then you can obtain a new model that is good at both tasks. So this is kind of the vanilla approach, and we have a better approach called Ratatouille that is have the same idea but with some additional tricks. Yeah, so here we are evaluating W, our model, and W is constructed based on two models, W1 and W2, lambda W1 plus 1 minus lambda W2, and actually we are varying only the lambda. So this is at zero cost. We don't have to do any additional training. We just say, yeah, we have two models, let's average them and evaluate their scores. If you look at the one in the middle, for example, so the first model is trained for captioning, so to describe images. The other model is trained to do detection, to detect object and the image. And what we can see here by varying the lambda is actually we can get good model that is both at describing and detecting the images at the same time. If you switch to the recent Ratatouille model, actually we can get even model better than the W1 and W2, which is also interesting. So this is for in distribution. And another aspect of this is when you do multimodal weight averaging, you get better generalization abilities on out of distribution tasks. So tasks that are not seen during training. And here again, for example, the one in yellow, the Ratatouille is significantly better than other models, even if we average multiple models. So it's not only two models, it's in this case and models. Yeah, so to recap, the technical takeaways is we show the importance of balancing the multitask training. Multimodal curriculum learning is efficient and leads to almost the same scores. Training on more modalities helps generalize two novel modalities. And we showed also that multimodal weight averaging is good in distribution and also in out of distribution setups. And maybe the main takeaway from this work is if the objective is to get more efficient models that can be trained and used in a reasonable amount of compute resources, I think the way to go is by working more on the training techniques, maybe rethinking the architectures, and of course the data quality. We have also a couple of other works related to this project, for example, EPALM and DPALM, where we try to adapt pre-trained LLMs, large language models, to do multimodal tasks. And the last one, EMA, which is a more researchy paper where we try to understand why actually LLMs or transformers in general can generalize to multiple modalities. Yeah, that's it. Thanks for your time.
Thank you, Mustafa, for your presentation with a lot of appetizer inside, vanilla and ratatouille. So does it inspire the audience for question? I'll let you find some question. In the meantime, I have one. I would ask the same I asked to the last presenter. In which part of the resources of the machine would you expect to have more effort and more power and potential to carry on this your science, because you're handling several type of media, some of them potentially very important in terms of size. So what are your expectations, recommendations, and what is the ideal machine?
Sorry?
Did you understand or just hear the question?
Yeah, can you hear me?
Yes, I can hear you, and everyone can hear you too.
Good. So yeah, I think that, yeah, the answer to the question is, and for this project and similar project, I think the bottleneck is GPU power. So if you have more GPUs, bigger GPUs, that would help significantly. We had actually a bottleneck or small issue for on the RAM or the CPU memory, because we are using multiple modalities, and usually the audio, the video, and images takes a lot of memory to load or to provide to the model. So sometimes we just use more GPUs to get more CPU memory. So I think this one, maybe now it's already solved, but usually it's good to have like twice the amount of CPU memory compared to the GPU memory on each node. There is also something related to the data set size, because sometimes the images are compressed, so that the amount of size is like a couple of terabytes of data, which should be fine on this cluster. But sometimes we have a lot of files, so a lot of images, a lot of text, and sometimes you are limited by the inode in each on the cluster. So this is also something I think is important for these large-scale projects.
Thank you for your rich answer.
Yep.
Any other question? It seems not. So thank you again.
Yeah, you're welcome.
Now, I think it's time for a short break. Short, well. So we start at 10:50, right? That's okay? Thank you.
Du coup, on va reprendre. La prochaine session, donc c'est une autre présentation sur la conduite autonome de la part de Valeo. Et c'est Spiridon Gildaris qui sera en visio et qui va nous présenter Foundation Models for Autonomous Driving.
Hello everyone, can you hear me?
Bonjour.
I don't know, can you hear me?
Yes, we can hear you.
And can you see the slides and the laser beam?
Yes, yes.
Okay, so hi everyone. I'm Spiros Gidaris. I work as a research scientist in Valeo AI, similar to Florent that presented earlier. And my talk today would be about how to leverage foundation models for 3D perception in autonomous driving. So before I start my talk, I will give some context about Valeo and this work. So Valeo is a top tier 1 supplier in automotive industry, and it has a long history in developing and providing sensors and software for autonomous driving assistance systems, so ADAS systems. For context, ADAS systems use sensors and cameras in order to provide cars with features like automatic lane keeping, so keeping the car on the same lane or maintaining a safe distance from the car ahead, or vehicle and vulnerable road users detection, so detecting other vehicles in the roads, or pedestrians or bikers, parking assistance, and so on. So in this context, Valeo, the last 30 years has shipped more than 1.5 billion sensors that are used for autonomous ADAS systems, and is also going to ship in the next 5 years another 1.5 billion sensors. And Valeo has a rich or diverse suite of sensors. It includes ultrasonic sensors, radar sensors, cameras, surround view cameras, long-range cameras, and LiDAR sensors, which would be more the topic of this talk, LiDAR sensors. So a few words about Valeo AI. So I think Flora already talked about it, but again, Valeo AI, we are 25 researchers, including PhD students, and we have collaborations with academic labs across France and Europe. And most of our presence is in France, but we have also a small presence in Prague. And we do research on topics related to autonomous driving, like perception or forecasting. And we are dedicating to open research. And by that, I mean our goal is to publish on top conferences like CVPR and NeurIPS, and release both our code and the models that we train. So we'll start about giving a very brief explanation of what are the foundation models. So a foundation model is any model that is trained on broad data and large volumes of data, and generally using annotation efficient ways of training, so self-supervised techniques. And after training, that can be adapted, for example, using fine-tuning to a wide range of downstream tasks, so which are the tasks that we are really interested to learn, to perform. So we'll give now like a very brief explanation of what is this pipeline of first training a large foundation model, and then fine-tuning on a downstream task of interest. So this pipeline essentially consists of two stages. So here in the first stage, we pre-train an image network using a self-supervised task. In this case, for simplicity, I use the image rotation prediction task. In this task, you take an image, you rotate it by either 0, 90, 180, or 270 degrees. You give each rotated copy to a network, to a neural network, and the neural network has to predict which is the rotation that was applied. So this is a self-supervised task in the sense that it doesn't require human annotation in order to provide the labels for this task, and it can be trained because of this reason with large volumes of training data, so raw training data. So, and the goal of this pre-training is that the network, in order to perform this task, it will have to learn the visual concepts that are depicted in the image, so that this is this specific animal and that is rotated. So, of course, this is an old, let's say, self-supervised task, a bit naive. Nowadays, there are much more better approaches, but I just gave it because it's simple to explain it. So after we pre-train the network in this way, during the first stage, we go to the second stage, where we adapt the network to the downstream task of interest. So this is the task that we really care to be able to perform. And that can be object detection or semantic segmentation. So in this case, we transfer the network as it is, we attach to it a new prediction head, and then we fine-tune it with the available annotated data. So the goal of this first pre-training stage is by employing it during the second stage, our network to reach much better performance on this downstream task of interest, or compared to not pre-training, not doing the pre-training, so compared to going directly to stage 2. Alternatively, you can think that the goal of the first pre-training stage is to require on the second stage fewer annotated data in order to reach the same performance compared to not having again the first pre-training stage. So in the team, we have a long experience, or we have many publications on how to pre-train image networks. Including the latest approach is MOCA, which we use actually the Ad-Astra GPUs in order to do that. But in this talk, I will not focus on how to pre-train image foundation models, but rather how to exploit them, how to further exploit them in order to learn on the second stage, in order to learn networks for that are more applicable tasks that are more specific to autonomous driving. In particular, my talk would be about how to exploit these pre-trained image foundation models in order to learn leader foundation models, leader neural networks. So cars, apart from cameras that are very often equipped with a lidar sensor. A lidar sensor actually is a sensor that emits laser beams in order to measure the distance of the objects that are around the eco vehicle, and essentially provide a 3D map of the scene. So like as you can see here. This is here, it's a car that moves in the streets. And these are the 3D point clouds that the LiDAR sensor has captured. And we have colored each point based on what is the semantic class of the action that it belongs to. So these points here belong to cars, the orange ones. This one, the green to vegetation. Here we have the road and so on. So the LiDAR sensor allow us to recognize, to perceive the objects that are around the ego vehicle, such as other vehicles, pedestrians, static objects, and so on. Also, it has an advantage that it provides precise distance measurements. So it allows us to know how far the other objects are in the street and what is their velocity, how fast they are moving. And compared to cameras, also another advantage that it has is that it can work also on night or low light conditions, because it doesn't rely the sensors to visible light in order to operate. So overall, the LiDAR sensor is often more robust or more efficient for 3D perception tasks in autonomous driving than cameras. However, in order to learn networks for the task of semantic segmentation in this case, so this here, the task that is visualized is semantic segmentation, where each point of the point cloud has a semantic label. So in order to learn this task, usually you require annotations for this task, which is that you have to annotate each point with a semantic label. But this is very extremely tedious, extremely time-consuming and expensive to perform. So, as I said, LiDAR data is tedious and costly to annotate. We would like to be able to learn LiDAR networks in a more annotation-efficient way. And in this talk, I will present you some methods of how to do that. I will start with the first work that was published on CPR 2022. This was actually a precursor of the work that was done using the Ad-Astra GPU resources. And actually, we did this work before we started using Ad-Astra, and then we used the Ad-Astra supercomputer and scaled this method. So in this approach, we leverage the fact that usually in autonomous driving dataset, you have both cameras and LiDAR sensors together, and that are usually synchronized and calibrated. So in this example that is coming from the new CINES dataset, the dataset has 6 cameras that you see here, and also a LiDAR sensor that captures a surround view point cloud. And as I said before, these 2 sensors are synchronized and calibrated, by which essentially I mean that you can take each 3D point of the LiDAR point cloud and you can project it to the 2D space of the 6 cameras, and thus establish a mapping between each 3D point to 1 or more 2D pixels in this camera. So a mapping with 1 or more cameras. So in this work, we leverage this availability of synchronized image and LiDAR data in order to pre-train 3D networks without using any manual annotation. So our approach, which is called image to LiDAR self-supervised distillation, consists of 2 steps. The first step is to pre-train 2D network. Actually, we don't perform this step, but we use off-the-shelf pre-trained image foundation models like Dino, Clip, and so on. The focus of the work was actually on the second step, which was to distill the knowledge of the 2D network, of the image network, to a LiDAR network. So the way it works is that, as I said, we have LiDAR data here and 6 cameras here that are synchronized. We have the pre-trained image foundation model, so the pre-trained image network, to which we give each camera frame, and we extract with it 2D features, so pixel-wise features. We extract a feature vector for each pixel in the 6 cameras. Then we give the LiDAR point cloud, 3D point cloud, to the LiDAR network, and extract with it a feature for each 3D point on the point cloud. Then the way we learn the LiDAR network, the image network is frozen, and the way we learn the LiDAR network is we have a contrastive loss that essentially enforces that the feature of a 3D point should be similar to the feature of the 2D pixel to which it corresponds to. So it should be similar to the feature of the 2D pixel that it has been mapped to. So thanks to this self-supervised image to leader pre-training strategy, we see that we are more data efficient for learning the downstream task of semantic segmentation of the new CINES dataset. In particular, in this experiment that I show here, we have pre-trained the network with our approach, which is called SLIDR, and using the entire new CINES dataset, the entire training set of the new CINES dataset, and then we fine-tune the pre-trained network on the task of semantic segmentation, of leader semantic segmentation, using either only the 1% of the available training data, or 5% of the available training data, or 10% of the available training data, 25, and 100%. And we see that thanks to this pre-training, we achieve much better performance than training from scratch directly on the downstream task, so the semantic segmentation of the point class using the same amount of annotations. Also, we see that as we decrease the number of annotations of the downstream task, so as we go from 100% to 1%, the improvement that our pre-training strategy offers is increases. And we have a similar observation, similar results for the downstream task of 3D object detection, again, using leader data. So this approach of self-supervised image to leader distillation is actually one of the best methods and most well-performing methods for pre-training leader networks. However, its gap compared to supervised learning is still quite big. We see here, for example, actually linear probing is a classic method for probing, for measuring the quality of the pre-trained representations. So in this experiment, after you pre-train your leader network, you freeze it, you don't train it anymore, but attach on it a linear head, a linear classification head for the task at hand, which is semantic segmentation. And you train only this head. And by doing that for this distillation methods and this approach that has been trained in a supervised way on semantic segmentation, we see that there is a large gap, performance gap between the best distillation approach and a supervised approach, which is more than 33 points. So in the next work that I'm going to present you now and was on CVPR 2024, and is the work that we use the Adastra GPU resources, we try to scale the previous method in order to close this gap. In particular, in this work, the first thing that we did was to simplify the previous approach, do some simplifications in order to make it more scalable, so we make it more easy to scale. And then we study 3 axes of improvement, 3 axes of scaling the approach. The first is using bigger networks that are trained on more training data, bigger image networks that are also, in this case, are the teacher networks. The second axis is scaling the 3D networks, so you're using bigger 3D networks, bigger leader networks. And the third axis is using more training data. And then, thanks to this improving on these 3 axes of improvement, we managed to have a method that improves the previous state of the art by more than 22 points and closing significantly the gap with the fully supervised case. So now the gap with the supervised approach is around 10 points. So this method is called scalar, and this is how it works. So first we did some simplifications compared to the precursor work, and that is now instead of having 6 cameras, so instead of at each training iteration using 6 camera frames, we only use 1, which we randomly select among the 6 available. So we randomly select 1 camera frame, and we also take the leader point cloud, not all of it, but only the part that is visible to this camera. And then, after we extract the 2D network pixel-wise features, and with this leader network pointwise features, we use a very simple cosine distance loss. So that is the feature that the leader network extracts for the 3D point should minimize the cosine distance with the feature that the 2D network extracted for the corresponding 2D pixel. So this make our method, compared to before that I didn't explain a lot, but it made it much more simple and easier to scale. Then we studied the influence of the three axes of scaling, which, as I said, is scaling the image network, scaling the leader network, and scaling the dataset. So we started by studying what is the impact of using bigger or scaling the 2D networks that we use. So we studied we use several 2D image networks that are pre-trained with different approaches, like Maya or Dino, and have different size, so different number of parameters, and have been pre-trained on different amount of data. And we saw using the Dino V2 approach, so using bigger networks like V-large of the Dino V approach, and it has been trained on much more data. 140 million images gave the best performance for the leader network. The next axis of scaling, the next axis of improvement was scaling the 3D network, so the leader network. In this work, we use an architecture called WAF-Lyron. It's actually a game from the team, and essentially it's based on the principles of transformers. We use this network and we scale it. And the way we scale it is for each, we increase the number of channels that we use for the feature of each 3D point. So in this case here, we use 96 channels. So feature vectors of length 96 for each 3D point, and then went to 256, 384, and 768, which is the biggest that we reached. And we see here that as we scale the network, we reach higher performance. We did here the same. This curve is again from our method, but with a bigger teacher. And again, we see as we scale the leader network, the gap with the supervised case is decreased. Now the final axis of improvement was the size of the dataset that we use for training. So it was custom before to train for these distillation approaches, to train on the same dataset that you will use for your downstream task. So for example, to train with a distillation way on the new CINES dataset, and then fine tuning on that. So each time you wanted to learn a leader network for a specific, pre-train a leader network for a specific task, you had to pre-train on the same dataset. But this is not in general the way that foundation models are used. The idea is to pre-train the foundation models or broad arrays of data, so to pre-train a single foundation model, and then only fine-tune it on a specific dataset and task. So in this case, we follow this approach. We use for this pre-training approach a mixture of publicly available datasets that are leader datasets that have captured with a diverse set or type of leader sensors. And we saw that thanks by training on these old datasets and then fine-tuning on each dataset specific, we arrived to much higher performance rather than having pre-trained on a specific dataset and fine-tuned on that specific dataset. So putting all this together, these three pillars of improvement, we got a method that achieves much better performance on several evaluation protocols like linear probing or fine-tuning using a very few labels, so 1% of the labels of new scenes, or using 1% of the labels of the semantic hidden dataset. So to conclude, we saw that it's important for in autonomous driving to have simple and scalable approaches for pre-training. Also, we saw that it's feasible to transfer representations across modalities. So in our case, from image to leader. And that actually data outside the autonomous driving domain, so data from internet, can improve a leader perception. Finally, we saw that the training over multiple datasets and sensor configuration also is a promising approach. And this concludes my talk.
Thank you for your presentation.
Thanks for your
Je
question.
français. Est-ce qu'il y a des questions dans la salle? Pas de questions. Donc, je pense que votre présentation était très claire. Ben, on va vous remercier encore du coup et on va passer à la prochaine présentation qui sera faite par Rita Rosner qui travaille à l'Université de Montpellier, donc pas très loin d'ici.
Thank you everyone. Bye bye from me.
Thank you. Et qui nous présentera une exploration exhaustive des mouvements collectifs du récepteur de la gréline.
Ah, okay. Bien sûr. So we are completely changing the topic now. In fact, now we are talking about proteins, more specifically membrane proteins. And I want to talk to you about how we used Adastra to exhaustively simulate G-protein coupled receptors. You might wonder, why would we do that? Why would we even care about that? Well, in preparation of this talk today, I had a look at my grandparents' medication list. What pills do my grandparents take? And what I found was they are taking a few pills against pain, some painkillers, against asthma, and against high blood pressure. And all those pills have one thing in common. They all target G-protein coupled receptors. In fact, 1/3 of all drugs on the market today target those proteins, which makes them consequently a super interesting protein family to study. And as chance would have it, that's also the protein family we are studying in our lab. And that's a group of researchers that work, like a few researchers in our group work computationally and the other half works experimentally. And we are working at the Institut des Biomolécules Max Mousseron here in Montpellier. Let me give you a bit of biological background on GPCRs. GPCRs are the largest family of membrane proteins, and among those, class A GPCRs are the most represented. All class A GPCRs look approximately similar. They have all a very similar shape. We call this in biology a conserved fold. And this conserved fold consists of 7 transmembrane helices, which basically allow the protein, the GPCR, to have access to, like, the GPCR is situated in our cell membrane, and it has access to the outside of the cell and also the inside of the cell, which will be important in a little bit. This is the GPCR we are working on in our lab. It is named after a little peptide, the ghrelin peptide, which binds to it and activates it. The ghrelin receptor is a very prototypical class A GPCR, and like this, it serves us basically more or less as a model system for all proteins of this family. The ghrelin receptor is mostly in our bodies, it's mostly expressed in the brain. The ghrelin peptide is produced in the stomach. Once the ghrelin receptor is activated by the ghrelin peptide, it's responsible for a plethora of physiological functions, starting from food intake over growth hormone secretion or reward signaling. And I'd like to explain a little bit how this activation process of the receptor actually works. Okay, no, that doesn't work. In its inactive state, the receptor has a so-called closed conformation, especially with respect to its intracellular region. I would like to point, but to its intracellular region, you see it. Okay, that doesn't work either. There. Once now a ligand binds to the receptor undergoes major conformational rearrangement, and especially with respect to this intracellular region, which opens up. And this now leaves space for intracellular protein partners, for example, the G protein, to bind. And once the G protein is bound, it initiates like a wave of signaling processes inside the cell. So to conclude, basically what we achieved is that we transmitted a signal in form of a ligand from the outside of the cell to the inside of the cell. And that's basically the job of our GPCR. Unfortunately, it is not as straightforward as that. In fact, the common hypothesis in our field is that GPCR activity is governed by conformational equilibria. That means that the receptor exists in many different states, which are in equilibrium with each other, whereby those states can exchange very quickly on a timescale of picoseconds, for example, but those exchanges can also take much longer on a timescale of, for example, milliseconds. Now, once different ligands bind to the receptor, those equilibria change. Some states might increase in energy, some states might decrease. And as a consequence of that, the response of our receptor to those different ligands is also different. And our goal was now, using Adastra, to find out how different ligands modulate exactly the energy landscape of our receptor, the ghrelin receptor. The working horse in our lab to answer all kinds of questions are molecular dynamic simulations, or short MD simulations. Maybe you know, but with MD simulations, it's quite easy to access or to sample fast processes on the timescale of picoseconds or nanoseconds, but it becomes much harder and sometimes even impossible to simulate longer processes. For us, long means on a timescale of microseconds to milliseconds. There is a way to overcome this hurdle, and this is by using enhanced sampling methods along so-called collective variables. What we do there is basically we bias our simulations along certain directions that are the collective variables to allow them to overcome higher energy barriers. And this way we can sample those longer processes on the timescale up to milliseconds, which we are interested in. This enhanced sampling is for, we implemented this enhanced sampling in a larger protocol, which we developed in the course of this project. It consists of principal component analysis in the first step, which we use to find directions along which we actually want to bias our simulations. Then in the second step, we perform those biased simulations, which are called metadynamic simulations. And in a last step, we perform Markov state modeling. And this last step actually allows us to get in high resolution the energy landscape of our receptors and how it's modulated in the presence of different ligands. But let's go through this step by step, starting with principal component analysis. We are quite lucky in the sense that we have an extreme amount of structural data on class A GPCRs. In fact, when we started this project about 2 years ago, there were 600 class A GPCR structures available, and they were experimentally resolved with, for example, X-ray crystallography, or now more and more cryo-EM microscopy. Now, actually, I think we have more than 1,000 class A GPCR structures. And the interesting thing is that those structures are not only resolved of different members of the protein family, but also of the receptors in different states and in complex with different molecular partners, different intracellular partners, as for example, G proteins, but also in the presence of different ligands. And we hypothesize now, since the shape of those class A GPCRs is very similar, also the motions which this shape allows for should be similar among all members of this protein family. And that, on the other hand, means that all those collective motions that GPCRs are able to do should be somewhat encoded in the experimental data. A powerful tool to extract those motions is principal component analysis, those collective motions. And this is actually also what we did. We used principal component analysis, or short PCA, which is basically a dimensionality reduction method, and performed this on all class A GPCR structures. And we actually got quite promising results. One of them you already see here. We see that PCA is in fact able to cluster inactive, active, and intermediate class A GPCR structures. That already hints at that the principal components we obtain might be might well describe the collective motions which are actually relevant for the GPCR activation process. Another thing we saw when we, for example, specifically looked at the motion which principal component 1 describes, we see that it describes an outward movement of transmembrane helix 6. You see this indicated by those little arrows, combined with a simultaneous inward movement of transmembrane helix 7. And as chance would have it, that is already a well-described activation motion of class A GPCRs. So basically, what we can conclude is that the principal components we obtain from principal component analysis well describe collective motions that are important for the GPCR activation process, and therefore may be good collective variables which we can use as directions for enhanced sampling. Which brings us to the next step in our protocol, the actual enhanced sampling simulations or metadynamic simulations. As already briefly touched on, the collective variables basically serve as directions along which we want to bias our simulations, though, so that we are able to overcome high energy barriers along the processes which we are interested in, so that we can basically simulate processes that have timescales of up to milliseconds. Nicely enough, metadynamics not only gives us, we performed metadynamic simulations on our systems, and nicely enough, for metadynamics, we do not only obtain our simulation data, but also we directly have access to the energy profiles of the systems we simulated. You can see one energy profile here. It's the profile of the ligand-free receptor, so the receptor in its apostate. And you can clearly see that this profile has two energy minima, which are separated by an energy barrier. And those energy minima correspond to inactive and active conformations, respectively. Now, what happens when a ligand, for example, the ghrelin peptide, is bound to the receptor? Well, we see not much changes, which is very unfortunate because we know that from experiments that the agonist, the ghrelin peptide, should actually increase the activity of the receptor. But good news, when we simulate the system, the receptor bound to an antagonist or inverse agonist, which are known to decrease or inhibit the activity of the receptor, we observe something very interesting. Our profiles get reduced to one energy minimum in the inactive, which corresponds to inactive conformations. That means basically that it's too costly for the receptor to transit to active states. So this corresponds very well to experimental data. What we can conclude from that, I think, is that metadynamic simulations, in the way we performed them, on the one hand, allow us to exhaustively simulate the conformational space of the ghrelin receptor in a ligand-dependent manner, but we are not quite able to quantitatively analyze the equilibria between different conformational states. And this is where Markov state modeling now comes into play. Markov state modeling is a mathematical framework which allows us to describe the energy or to calculate the energy of different states and the transitions between them. However, the important thing to know with Markov state modeling, we cannot perform this on our metadynamics data. We actually have to perform unbiased standard MD simulations. So what we did is we took representative models from our metadynamic simulations and launched a lot of unbiased MD simulations. And upon those MD simulations, we constructed Markov state models. You can see one result of this on that slide. You see the energy landscape of the ligand-free receptor on the left, the APO receptor, and then how the energy is modulated once an agonist bounds or an antagonist or an inverse agonist. Just for clarity, the regions you see in blue are low energy regions, and the regions you see in red are high energy regions. Maybe when we want to dig a little bit deeper, let's start with the simplest case on the right-hand side. You see when the inverse agonist is bound to the ghrelin receptor, we only basically see one low energy basin, which corresponds to only one state. So that when an inverse agonist is bound, the receptor is only able to populate one state, and this state is a distinct inactive state we already know from X-ray structures. Now let's move on to the more interesting cases when the receptor is in its apo form or when an agonist or antagonist is bound. We see here that the receptor is actually in all three cases able to populate multiple metastable states. And interestingly, in all three cases, the receptor is able to populate an inactive state, which we also know from experimental structures, but it's different than the inactive state it would populate when the inverse agonist is bound. This inactive state I marked here in dark blue. What we also see that the receptor is able to populate an active state, which we know from experimental structures, when it's in its apo form or when the agonist is bound. However, we are not able to, or the receptor is not able to populate the state when an antagonist is bound. Our Markov state models not only allow us to find out which metastable states we populate for those different systems, but it also allows us to calculate actually the energies of those states or the population percentages, let's say. And what we see is in blue, again, we have the inactive state. The inactive state is the main state in the apo system, but once an agonist binds to the receptor, the inactive state decreases in population, whereas the active state increases in population, which again is super congruent with experimental data, because we know an agonist is responsible for receptor activation. When an antagonist is bound, the receptor is 50% in its inactive state. Another interesting thing we can obtain from Markov state modeling is actually the speed of the transition between different states. And we see, for example, that when the receptor is ligand-free in its apo state, the transition from the inactive state to the active state takes us 80 microseconds. You already see we would never ever have been able to simulate this with standard MD simulations. But interestingly, now an agonist binds, this transition, the mean time it takes for the receptor to transition gets divided by 4. It's way faster, which is also, again, super congruent with experimental data. You might have already been wondering what are those states I did not talk about this far. Well, they are not known. We do not have any experimental structures which correspond to those states, but our analysis actually show that they are intermediate states. One of those intermediate states you see here in green. It is only populated when the receptor is in its apo form, in its ligand-free form, and our simulations show that it's responsible for ligand binding. Another intermediate state is the one you see here in blue. It is different with respect to the intracellular side, and we hypothesize that this state is important for G-protein coupling. So I hope I have convinced you that with our Markov state modeling and in fact with our whole protocol, we are actually able to compute the energy landscape of the ghrelin receptor and also to capture the effect of different ligands, of pharmacologically distinct ligands. This all would not have been possible without the computing resources of Adastra. And you see here, in the scope of the Grand Challenge, we used almost 800,000 GPU hours, most of them actually for Markov state modeling. The metadynamics part was the smaller part, but we used 600,000 GPU hours for the unbiased simulations upon which we constructed Markov state models. Just to give you a bit of an outlook, there are quite a few projects which piggybacked off of those results. For example, we are trying to adapt the pipeline to coarse-grained model to make it more computationally efficient. But another very interesting thing I find, which we currently started doing, is we are designing novel proteins, de novo proteins, which bind to the different conformations we found during our Markov state modeling. We are using deep learning for this, so AI, more specifically a method that's called Bindcraft. It's a deep learning algorithm which uses AlphaFold weights. And with that, I would like to thank you for your attention. I would like to thank GENCI for the computational resources provided and CINES for their work with and for Adastra. And last but not least, my team, especially Nicolas Floquier and Maxime Louet, who are my thesis advisors. Thank you very much.
Thank you for this very interesting presentation. So are there any questions?
I have a question because you mentioned the time you spent on Adastra to run these simulations. Do you have an idea of how long that would take if you only had access to CPUs? Or if that would even be feasible with only CPUs?
I would say it's not feasible. I think the GORMEX is way faster on GPUs, especially for all Adam simulations. So I would say it's basically not feasible with only CPUs.
Thank you.
Other questions? So thank you very much on this. So the next presentation, je vais rebasculer en français, sera faite par Nicolas Boisard. Je ne sais pas si il est présent. Oui, c'est toi. OK. Et donc là, c'est un grand challenge qui a tourné sur la partition APU d'Adastra, donc sur les MI 300. Et il va nous présenter une présentation sur les polyglottes français et européens, encoders and retrievers, avec utilisation de données synthétiques. Et vous êtes deux, finalement, avec Hippolyte Tissereau. Okay.
Bonjour à tous, merci de nous recevoir aujourd'hui, merci d'être aussi nombreux. Donc aujourd'hui, déjà je vais me présenter, je suis Nicolas Boisard, il y a Hippolyte Tissereau-Boutlef avec moi. On va vous présenter notre projet qui a été rendu possible grâce aux APU MI 300 proposés par Adastra. On les remercie. Donc c'est un projet, c'est un modèle de type encodeur. Donc déjà, premièrement, je vous propose de voir ce qu'est qu'un modèle encodeur. Donc, vous n'êtes pas sans savoir, je pense qu'aujourd'hui, on parle beaucoup des modèles décodeurs, donc des modèles qu'on dit génératifs, donc qui prennent en entrée du texte et ressortent en sortie du texte. Nous, on a travaillé sur un modèle encodeur, donc quant à lui, il prend du texte en entrée et en sortie ressort une représentation vectorielle de ce texte. C'est pour ça qu'on les appelle encodeurs, parce qu'ils vont venir encoder en fait la phrase sous forme vectorielle. Faut savoir aujourd'hui que en fait, les modèles encodeurs, ce sont les modèles qui sont peut-être le plus utilisés en industrie, le plus utilisés pour le plus de use cases possibles, puisqu'ils sont à la fois légers et rapides. On les retrouve par exemple pour de la classification. Donc en fait, par exemple, si vous avez, je sais pas, un commentaire sur Internet, dire s'il est positif ou négatif, on peut aussi le retrouver pour de l'extraction. C'est-à-dire que vous allez avoir un document, vous allez vouloir récupérer par exemple toutes les adresses email ou les numéros de téléphone dans ce document. On a aussi un cas d'usage qui est un petit peu, on va dire, à la mode en ce moment, c'est le retrieving. Par exemple, vous avez une base de données avec beaucoup de documents. Vous allez pouvoir faire une recherche, comme un moteur de recherche sur ces documents.
Je ne sais pas si c'est possible, peut-être. Moi, je l'ai sur mon ordinateur, je peux faire une présentation de Zoom ou l'original, ouais. Je suis désolé de t'avoir interrompu, mais pour moi, c'était un point important.
Donc, voici pour les cas d'usage. Donc maintenant, on peut se demander pourquoi en fait on veut faire un encodeur en 2024. Tout simplement parce que le dernier encodeur qu'on appelle Backbone, donc celui qui est un peu le parent des différents projets que la communauté effectue aujourd'hui, a été sorti en 2021. Il s'agit de Deberta, donc, qui a été créé par Facebook. Et en fait, depuis 2021, principalement, les projets de recherche sont plutôt portés sur des décodeurs. Donc nous, notre idée, elle est assez simple, en fait. C'est comment on peut ramener toutes ces nouveautés qui ont été faites avec les décodeurs ces 3 dernières années sur les encodeurs. Donc ça, en fait, ça passe par 2 grosses étapes, notamment, par exemple, le training. Aujourd'hui, on a des données, des tailles de corpus bien plus importantes que ce qui existait en 2021, notamment grâce aux décodeurs. On a aussi des données de meilleure qualité. Il y a une relation assez simple sur les performances et la qualité des données. Plus la qualité est bonne, plus les performances sont élevées. Et puis aussi, on a des nouveautés au niveau de l'architecture, donc on y reviendra un petit peu après, sur la façon de concevoir notre modèle avec les dernières nouveautés. Notre vision également, elle est d'avoir un modèle le plus généraliste possible, donc pour pouvoir couvrir le plus de tâches, que ce soit, donc comme je vous ai dit, du retrieving, de la classification. On est également parti sur un modèle multilingue, donc avec 15 langues, notamment les langues européennes et également les langues les plus parlées dans le monde. Et très important, on a voulu que notre modèle soit complètement open source, c'est-à-dire qu'on va on va distribuer tous les checkpoints, donc tous les points de sauvegarde de notre modèle qui ont été effectués durant le training, ainsi que le modèle final, et la base de code qu'on a utilisée, spécialement conçue pour les AMI 300, donc pour tourner sur APU. Donc, maintenant qu'on a une vision un peu globale de pourquoi l'encodeur, on va se pencher sur comment on entraîne un encodeur en 2024. Nous, on a divisé notre entraînement en 3 grandes parties. Ce sont 3 grandes parties qu'on retrouve notamment sur les décodeurs. Donc, il s'agit de la première du pré-training, du post-training et du fine-tuning. Et très important, pendant toutes ces parties, on essaye aussi d'évaluer en continu afin d'être sûr que notre modèle ne divague pas et aille dans la bonne direction. Donc, commençons avec le pré-training. Donc, ce qui est très important dans le pré-training, c'est les data, et c'est notamment le moment où le modèle va avoir la plus grande quantité de data. Nous, on est parti sur un mix de data de 5 trillions. Donc, pour vous donner une idée, 5 trillions, en fait, c'est le nombre de mots, de tokens que l'AMA 3, donc le dernier modèle de Facebook, a vu. C'est un corpus vraiment conséquent. On a notamment mis 40% en anglais et 40 autres pourcents pour les 15 langues restantes, et notamment 6% en français, 6% en allemand, qui représentent à peu près 400 milliards de mots, qui est bien plus que Deberta et les encodeurs actuels ont vu en français. Donc, il y a également une relation assez simple, c'est plus on voit de français et plus les performances seront bonnes en français. Donc on aura des performances bien meilleures que ce qui existe actuellement en français. On a également décidé de mettre des mathématiques. Les mathématiques, c'est assez simple, c'est que la raison, en fait, on a vu ces dernières années que quand on mettait des mathématiques, ça permettait d'avoir des capacités qu'on appelle émergentes. En fait, ça va être les capacités pour que le modèle puisse raisonner. C'est-à-dire, si on lui donne des questions un petit peu complexes, le modèle va être capable de raisonner. Et ça passe notamment par incorporer des maths durant l'entraînement. Dernier point intéressant, on a aussi rajouté des langages de programmation, donc 42. Forcément, le ratio est un peu plus élevé pour les langages de programmation les plus courants, donc C++, C. Ça vient du fait qu'il y a aussi plein de cas d'usage qui demandent les langages de programmation. Donc maintenant qu'on a vu l'aspect général des data, on va pouvoir parler un petit peu du modèle. Nous, on a fait le choix de partir sur 2 modèles. Un modèle de 300 millions de paramètres, un autre de 2 milliards. La raison est simple, c'est qu'un 300 millions est extrêmement rapide, on va dire, à l'inférence, donc au cas d'usage de tous les jours, et également plus rapide à l'entraînement. Et le 2 milliards, quant à lui, sera un petit peu plus lent, mais par contre, aura des meilleures performances. Ça, c'est un choix du cas d'usage de chacun. L'autre avantage aussi du 300 millions, c'est qu'il est plus rapide à entraîner, et donc on peut continuellement faire des expérimentations dessus, ce qu'on ne pourrait pas faire avec un 2 milliards parce que ça nous prendrait trop de temps. Comme je vous ai dit, on a également rajouté donc, des choix architecturaux qui étaient faits dans les décodeurs. Je ne vais pas rentrer dans tous les détails. En tout cas, il y a un point qui est important, c'est ce qu'on appelle la taille du contexte. En fait, c'est la taille du document que vous allez pouvoir passer à votre modèle. Deberta, donc le dernier modèle en date encodeur, il était plafonné à un document de taille 2048. Nous, on allait bien plus loin. On va aller jusqu'à 16 000. Ça, c'est pour des cas d'usage, donc comme je vous ai dit, de retrieving, etc. On voit qu'aujourd'hui, une taille de 2000, c'est trop petit pour un document. On a besoin d'aller au-dessus. Donc maintenant qu'on connaît les datas, on sait un petit peu comment notre modèle est structuré, on va se demander comment on l'entraîne. Donc en fait, les modèles encodeurs, c'est assez simple. On a une phrase, on va venir masquer un certain ratio de mots dans cette phrase, donc ici 2. et on va demander à l'encodeur de les retrouver, de les démasquer. Et en fait, l'encodeur, pour démasquer ces mots, va avoir besoin du contexte général de la phrase. Et donc, en ayant le contexte général de la phrase, on l'entraîne également à faire une bonne représentation de cette phrase, ce qui est exactement le cas d'usage qu'on veut à la fin. Nous, dans notre cas, on a vu qu'on pouvait masquer jusqu'à 50% des mots. Comment on a choisi ce chiffre? On l'a pas sorti par hasard. En fait, c'est très simple. On a fait ce qu'on appelle les scaling laws, donc des expérimentations. On a fait varier le masking ratio progressivement. Et on a vu qu'en fait, on obtenait les meilleurs résultats avec 50 et qu'au-dessus, on avait ce qu'on appelle de l'instabilité, c'est-à-dire que le modèle ne s'entraînait plus correctement. Dernière information, c'est au niveau des optimisations de code. Je ne vais pas rentrer dans tous les détails. En tout cas, si j'avais un point qu'il faudrait retenir, c'est qu'il y a une optimisation extrêmement simple dans PyTorch qui marche pour tous les sujets, donc que ce soit pour de la computer vision ou du texte. C'est ce qu'on appelle compile en PyTorch. C'est une ligne de code. Je vois rarement dans les projets l'utilisation de cette ligne. C'est vraiment une ligne. Je vous conseille de l'activer. Ça vous fait gagner donc, en performance et aussi en batch size. Batch size, c'est la quantité de données que vous pouvez donner par étape à votre modèle lors de l'entraînement. Ça ne coûte pas grand-chose. Moi, je vous conseille de le faire. Après, si vous avez des questions plus profondes sur comment optimiser le code, n'hésitez pas à venir nous poser des questions. Je ne vais pas rentrer dans les détails parce que ça prendrait trop de temps, mais si vous avez des questions à la fin, n'hésitez pas.
Ok, bah maintenant que Nicolas nous a parlé de la partie pré-entraînement du modèle, je vais passer un petit peu de temps à vous expliquer comment on évalue ce modèle, en tout cas en l'état. Pour l'instant, je vais vous présenter l'ébauche entre guillemets d'évaluation qui nous permet d'être suffisamment flexible pour pouvoir faire des évaluations rapides et un peu à tout moment, parce qu'un benchmark d'évaluation en sortie, c'est quelque chose d'assez gros, c'est quelque chose d'assez coûteux en termes de calcul, rien qu'à l'inférence. Et nous, notre objectif, en fait, c'était de se dire, on veut pouvoir évaluer nos modèles rapidement, à beaucoup d'instants, sur beaucoup de checkpoints différents, tout en ayant la capacité à avoir des takeaways qui soient suffisamment exhaustifs. Donc, en gros, on a designé un micro-benchmark, on va dire pour le moment, qui est inspiré du MTEB, sur lequel on a sous-sélectionné 4 tâches principales. Alors, le MTEB, pour donner un peu de contexte, c'est un benchmark assez classique pour l'évaluation des modèles encodeurs. Donc, on vient évaluer les embeddings sur un certain nombre de tâches en zéro shot. Donc, ça va être du clustering, du retrieval, du re-ranking et de la classification. Ça, c'est pour les 4 tâches qu'on a retenues. Et aussi, pour pouvoir être suffisamment synthétique dans la phase d'évaluation, on a retenu 2 langues principales, l'anglais et le français, qui sont à notre sens assez parlantes. Et sans plus attendre, donc voilà les premiers résultats qu'on obtient sur nos modèles. Alors, pour vous donner encore une fois un peu de contexte, là, c'est une évaluation de notre modèle 300 millions. Notre modèle à 2 milliards de paramètres, il est encore largement dans sa phase de pré-entraînement. La loss est encore beaucoup en train de descendre, donc ce ne serait pas forcément très intéressant de voir où il se situe par rapport à l'état de l'art aujourd'hui, ce qui serait probablement encore un peu en retrait. Mais pour ce qui est du 300 millions de paramètres, depuis le début des Grands Challenges, on a quand même eu le temps de le traîner assez copieusement. Même si on en est à peine plus de la moitié, on commence à voir la loss qui se stabilise progressivement. Et donc ça, c'est pour les évaluations sur les 4 tâches dont je vous ai parlé. Si vous regardez, en fait, on s'est comparé à 2 modèles, à savoir des modèles de la gamme XLM Roberta, qui sont des modèles bien connus dans le monde des encodeurs, le base et le large, qui sont tous les deux, si vous le remarquez bien, plus grands que notre modèle, assez significativement. Et sur l'anglais, en fait, on bat systématiquement le modèle base, ce qui est plutôt positif, et même parfois, sur certaines tâches, on bat les deux. Pour ce qui est du français, on voit qu'on est peut-être un tout petit peu moins bon en comparaison, mais on arrive sur une tâche notamment à être meilleur que XLM Roberta Base. Et pour ce qui est du reste, en fait, on voit qu'on est quand même on est largement dans les clous, on est quasiment à égalité avec XLM Roberta Base pour un delta de nombre de paramètres qui est quand même conséquent. 60 millions, c'est pas rien pour ce type de modèle. Donc encore une fois, je précise, notre pré-entraînement n'est pas encore terminé. Donc on espère en fait pouvoir combler ce gap qu'on a avec les modèles XLM Roberta pour les langues et les tâches qui sont concernées. Mais on a bon espoir de ce point de vue-là. Alors maintenant, je vais vous parler un peu des prochaines étapes. Donc les 2 gros checkpoints qu'on a jusqu'à présent, donc c'est le pré-training qui est encore en cours certes, mais qui côté code base, côté implémentation, etc. est achevé, on peut le dire. Côté évaluation, pareil. Ce qu'on fera en sortie, c'est qu'on scalera notre évaluation à davantage de tâches, à davantage de langues, mais grosso modo, il n'y aura pas grand-chose à rajouter de ce point de vue-là. En revanche, il reste quand même 2 étapes fondamentales pour pouvoir sortir un modèle en bout de ligne. C'est le post-training et le fine-tuning. Donc, je vais vous parler... Alors, pardon, excusez-moi. J'ai oublié l'annealing aussi, qui était à gauche de la... Hop. Voilà, à gauche, il y a une deuxième phase dans le pré-training qui s'appelle l'annealing, dont je vais vous parler tout de suite. Alors, l'annealing, en fait, c'est exactement pareil que le pré-training, dans le sens où c'est le même objectif d'entraînement. Donc, c'est ce que Nicolas a présenté tout à l'heure avec l'encodeur qui essaie de démasquer des mots qu'on a masqués aléatoirement dans les inputs. Donc, l'objectif est le même, sauf que là, l'objectif, ça va être de donner des données de très très bonne qualité à notre modèle et de faire décroître le learning rate progressivement jusqu'à 0. Et ça, c'est des apprentissages qu'on a récupérés des modèles génératifs et on a montré que ça a amélioré très clairement les performances parce qu'en fait, l'idée, c'est on va donner des données de très bonne qualité à notre modèle et c'est les dernières choses qu'il aura vues. Donc, ça a fait ses preuves, en tout cas, dans le monde des modèles génératifs. Et voilà, donc grosso modo, c'est la deuxième étape du pré-training qu'on a envie de conduire et qui va arriver très bientôt, qui est déjà en cours, on fait des expérimentations dessus. L'étape d'après, une fois qu'on aura notre modèle après l'annealing, on pourra dire qu'on a notre modèle backbone, notre modèle pré-entraîné, et là, les objectifs d'entraînement changent. On n'est plus sur du mask language modeling, comme on en a parlé dans les précédentes slides, on passe sur un training contrastif. Donc c'est ce qu'on a appelé ici le post-training, et en fait, l'idée, c'est de venir apprendre à notre modèle des représentations de phrases de meilleure qualité. Pour vous donner une idée, les données auxquelles on a accès pour cette partie post-training, c'est des données sous forme de paires, des données semi-supervisées. On va avoir des paires positives et des paires négatives. Le but, ça va être de rapprocher les paires positives dans l'espace latent, d'éloigner les paires négatives dans l'espace latent pour améliorer la compréhension, la capacité de compréhension et d'encodage des phrases de notre modèle. Donc pour l'instant, où est-ce qu'on en est ? On a passé pas mal de temps sur une partie de data collection. On a autour de 1 terabyte de données dans les 15 différentes langues qu'on a utilisées dans notre pré-training, ce qui est une quantité quand même non négligeable si on rapporte ça aux 30 terabytes de données, d'une trentaine de terabytes de données qu'on a pour notre pré-training. Et côté processing, voilà, il a fallu qu'on convertisse ça au bon format. Donc ça n'a pas été complètement trivial, mais maintenant cette étape est passée. Pour ce qui nous reste à faire, il reste encore du processing à faire. Notamment, ce qu'on voulait faire, la principale chose, c'est faire du quality filtering sur nos données. Ça, pareil, c'est des takeaways qu'on a de l'entraînement des modèles génératifs. Filtrer la qualité de nos données, ça permet vraiment d'améliorer les résultats en bout de chaîne de notre modèle. Parfois, il vaut mieux avoir moins de données de meilleure qualité que plus de qualité un peu moyenne. Évidemment, la dernière étape, ce sera de faire le fameux post-training contrastif une fois que toutes les données seront récoltées et processées. Et en bout de ligne, une fois qu'on aura notre modèle post-train, donc avec une bonne compréhension au niveau de la phrase, une bonne capacité à encoder des textes plus complexes, eh ben, on aura la possibilité de faire un fine-tuning. Alors là, le fine-tuning, il est vraiment spécifique à la tâche qui nous intéresse. On peut avoir des fine-tuning pour de la classification, pour de la word recognition, du scoring, du Q&A, etc. Donc en fait, grosso modo, ce qu'on veut sortir, nous, c'est une fois qu'on a notre modèle post-train, qui est un seul et même modèle, on pourra construire des versions de ce modèle, donc l'un qui soit spécialisé en classification, l'autre en identity recognition, par exemple, etc., etc. Et ça nécessite beaucoup moins de données que toutes les étapes préalables. C'est des choses même que les particuliers, enfin, les académiques / les industriels pourront faire de leur côté avec leurs données. Et ça, c'est vraiment en bout de chaîne ce qu'on a envie de faire une fois que les 2 premières étapes de pré-training et de post-training seront terminées. Donc voilà, c'est en conclusion quelques photos de l'équipe qui a travaillé dur sur ce projet et qui continue de travailler encore aujourd'hui évidemment dessus. Alors nous, on est extrêmement enthousiasmés à l'idée de continuer à travailler sur ce projet. Il nous reste quand même pas mal d'étapes. On a fait un bon bout de chemin déjà. On a des résultats assez intéressants. On espère pouvoir aller au bout en tout cas. C'est pas la motivation qui manque. Donc évidemment, n'hésitez pas si vous avez les moindres questions, que ce soit ici ou plus tard, de manière un peu plus informelle. On se fera un plaisir d'y répondre. Merci beaucoup.
Merci à vous deux pour cette présentation. Est-ce qu'il y a des questions dans la salle? Oui.
Bonjour, merci beaucoup pour la présentation. J'ai une question, enfin, si je peux, mais déjà, je vais commencer par une. Combien ça vous a coûté de faire l'entraînement sur les cartes M1300 et est-ce qu'il y a eu vraiment un changement par rapport à l'utilisation d'une autre génération de cartes? Ça.
Sur le coût exact, on va dire en termes d'argent, je ne le connais pas. En termes nombre d'heures, le gros modèle va coûter à peu près 220 000 heures. Ce qui est la différence entre les MI 250 et les MI 300, c'est surtout un gain de vitesse. Donc au niveau d'argent, je connais pas la différence entre le
Non,
coût pour
je
une
parlais d'heures, de toute façon.
Okay. Pour les MI 300, on a un gain de vitesse. On a aussi un avantage sur la taille. Donc c'est un petit peu technique, mais sur la taille de la RAM en GPU. C'est pas de la RAM vu que c'est des APU. Donc, pour faire simple, je dirais de la RAM. Ça nous permet de donner plus de données et d'avoir un modèle plus gros. Donc ça, c'est surtout le principal avantage qu'on a eu en tout cas avec les MI 300, c'est de la vitesse et une batch size plus importante.
Et ma deuxième question, du coup, c'était par rapport à la comparaison que vous avez faite avec les deux autres modèles. Quand vous montrez 5% de différence d'effort, est-ce que c'est vraiment significatif pour l'utilisateur de faire 5% de mieux, en fait, pour quelqu'un qui n'est pas très regardant par rapport aux résultats sur l'IA, sur des choses comme ça?
Non, mais très, très bonne question. C'est vrai que la question de la statistical significance des résultats en NLP de manière générale, elle est souvent mise un peu de côté. Là, elle est en train de revenir un tout petit peu plus sur le devant de la scène parce qu'on réalise que les deltas parfois qui sont montrés dans les benchmarks ne sont pas significatifs. Là, en l'occurrence, on ne s'est pas vraiment posé la question de si on était sur une statistical significance ou pas. De toute façon, le modèle qu'on évalue là, il n'est même pas fini d'être pré-entraîné. C'est juste pour avoir un ordre d'idée, savoir si on est dans les clous. Donc, alors, on voit qu'il y a certains deltas qui sont plus importants que d'autres. En fait, le takeaway le plus intéressant de ce tableau, c'est de montrer qu'on est dans le jeu. Voilà, on est dans le jeu et on n'a pas fini de pré-entraîner notre modèle. Sur des langues importantes comme l'anglais et le français, on est en moyenne au niveau, voire un peu au-dessus. Est-ce que c'est statistically significant ou pas? Ça, c'est des choses qu'on fera de manière un petit peu plus précise au moment où on aura notre dernière version de notre modèle et on essaiera vraiment de montrer de manière exhaustive sur plus de langues, sur plus de tâches. Et aussi, là, on parlera de statistical significance pour pas mentir aux utilisateurs et leur vendre une amélioration qui n'en est pas une. Mais non, très bon point. Pour être honnête, non, là, pour l'instant, on ne s'est pas intéressé à ça. C'est pour savoir si on est dans les clous. Et la réponse, je pense, avec ces graphes, c'est plutôt oui.
Ouais, moi j'ai une question, c'est par rapport aux données d'entraînement, parce que vous les avez beaucoup mentionnées, que vous les avez triées, mais je me demandais l'origine des données, d'où vous les avez tirées.
Ouais. Alors, pour l'anglais, je peux te donner les datasets. Pour l'anglais, c'est FineWeb, les datasets release par Hugging Face. Pour les autres langues, on a choisi Cultura X. C'est un dataset assez conséquent, peut-être de 20 trillions, qui regroupe une centaine de langues. Nous, on a fait le choix de ces 15 langues. Pour les mathématiques, on a utilisé... ok, je me souviens plus du nom exact, je pourrais te le donner après, je l'ai noté. Proofpile. Et pour les langues de langage de programmation, on a utilisé The Stack, qui est aussi un dataset de Hugging Face. Donc et les données parallèles, j'en ai pas parlé, mais ça vient d'une entreprise qui s'appelle Unbabel, qui a release un modèle qui s'appelle Tower, qui est spécialisé dans la traduction. Ils ont également, alors je sais pas s'ils ont encore distribué les données parallèles auxquelles je parle. En tout cas, je sais que ça va apparaître, ils vont les release. Ça sera à voir avec Tower. Et voilà, je sais pas si j'ai répondu à ta question. C'est que des données open source. Tout est open source. Non, les parallèles, pour l'instant, elles ne sont pas distribuées, mais elles le seront. Elles sont peut-être même distribuées, en fait. Je ne suis pas au fait des dernières nouveautés de leur projet, mais je sais que ça arrivera, en tout cas.
Moi, j'ai une question. Merci d'abord pour votre présentation pédagogique et enthousiaste. Pour comparer des choses comparables, est-ce que dans vos communautés, on s'intéresse, pour comparer des approches, aux aspects sobriété? Sous-entendu, bon, on va comparer une performance, un résultat, mais à un moment donné, est-ce que vous avez pour intention de dire, bon, on obtient ça avec un entraînement qui a un coût énergétique de temps, et est-ce qu'il y a de gros écarts entre les communautés, puisque à l'échelle internationale, tout le monde n'a pas accès aux mêmes infrastructures?
Alors, pour répondre assez Assez concrètement, les conférences de NLP aujourd'hui sont assez regardantes de ce genre de sujet. Il y a souvent des bons points, on va dire, qui sont attribués aux méthodes qui sont sobres sur le plan computationnel. Nous, on a fait le choix, évidemment, de faire un tracking de tout ça, mais pour l'instant, comme ce n'est pas les priorités, notre objectif, c'est vraiment l'entraînement, avoir les performances les meilleures possibles, tout en ayant évidemment un regard là-dessus. Quand on écrira le papier final, le rapport technique, évidemment que tout ça, ce seront des sujets qui seront abordés dans des parties bien dédiées. Et donc oui, non, pour répondre à la question de manière simple, c'est oui, il y a un vrai intérêt autour de ça. C'est souvent très valorisé dans certaines conférences, notamment les conférences de la classe ACL, conférence Association for Computational Linguistics, qui valorise énormément ce genre de choses. Donc oui, il y a quand même un vrai intérêt porté autour de ces sujets. Mais voilà, en toute honnêteté, pour le moment, on n'a pas fait l'effort d'avoir des graphiques précis pour rendre compte de ces sujets-là, mais c'est quelque chose qu'on a prévu de faire.
Bon, ben, s'il n'y a plus d'autres questions, merci encore pour votre présentation.